All right, we should be coming on. Hopefully everybody's seeing the screen. Welcome everyone, and thank you for joining us for the launch of Harrington's Masterclass series. We created this series to share, technical expertise that Harrington specialists bring to our customers every day in a format that reaches a broader audience. These sessions are designed to be practical, focused, and actionable. Today's topic, slash your cooling tower costs with advanced filtration. We estimate that 20% of cooling towers operate without filtration, and so many more with inadequate systems. The opportunity to reduce maintenance costs, improve efficiencies, and extend equipment life in this case is significant. We'll kick things off with a short, brief overview of Harrington from our marketing director, Peter Ryan. Then we'll dive into the technical session with two of our top filtration specialists, Ron Saval and Samantha Stahl. We're excited to kick off this series and look forward to sharing insights that can help you improve your operations and bottom lines. A few housekeeping things before we get started. We're going to keep everybody muted during the session and even after the session, keep things on track. What we will do is open up the question and answer box. So during the presentation, if you have a question, you can type it in. We'll try to answer a few as we go, but we'll probably save the 15 minutes after the session and answer as many of those questions as we can. So with that, why don't we advance the slide, Ron, and we'll give a little introduction. Kind of went through this, so you guys will be listening only, and you can submit your questions in the Q&A. Next, Ron. So our speaker today, our main speaker, is Ron Saval. Ron's a Harrington filtration subject matter expert with over 40 years experience in the industry. That qualifications, he has industrial experience in municipal, industrial, commercial markets. His expertise spans applications from water and wastewater to semiconductor and, of course, cooling towers. Samantha, who's going to be supporting Ron with Q&A and backup, she's a filtration specialist for Harrington for the Upper Midwest and the Great Lakes region. Samantha brings over 18 years experience in process and HVAC filtration. As with all of our filtration and all the Harrington specialists, they're known for their hands-on approach and problem-solving expertise. So with that, Ron, let's advance it. And Peter, I'll let you take over.
Great. Thanks so much, Kevin, for the introduction. And first of all, thanks everybody for joining us today. Really excited to have you here on the first of our masterclass series. And we think the content is really going to be interesting and useful to you, as well as really looking forward to hear your questions at the end. So a little bit about Harrington to start us off. The key thing about Harrington is that we focus on providing end-to-end flow control solutions. That's a fancy way of saying that we have products and capabilities in our organization to take care of every piece of the flow control, every piece of the flow control application in your facility, whether it be pumping, filtration, tanks, valves, pipes, et cetera, et cetera. I've been with the company a little over a year now, and one of the things that I've noticed is in a lot of cases, Harrington is equated with pipes. People think, Harrington plastic pipes, and they don't realize that we have such a broad breadth of capabilities and solutions that we can bring to bear. The other piece of it is being highlighted by Samantha and Ron here today, is that we don't have just the products, but we have an incredibly talented stable of people in our organization that know your applications, know the products, and understand how you're being challenged every day and how to help you solve those problems. So we have the expertise and we have the products to implement solutions for you and to help your operations keep the operations running smoothly and efficiently. Next slide. The key here on this piece of it is not only the expert guidance and the solutions that I talked about, but we also are really masters of supply chain solutions. Harrington has inventory. We don't have a problem stocking inventory, and we create custom supply chain solutions for all of our customers. We have customers that order from the local offices. We have customers that have vendor managed inventory in their facilities where we bring the products that they need into their facilities and we manage them to make sure that they never run out. We also have programs where we will stock custom inventory locally. So our services include not only what we sell and the expertise to pick the right things, but whatever mechanisms and logistics help that you need to make sure those products are fully available to you exactly when and where you need it, so that you never have any risk of downtime and that things keep humming smoothly in your facility. Next slide. A little more underscoring about our technical specialist capabilities. Obviously, Ron and Samantha are here for filtration, but we do have teams of specialists within the organization. We have specialists for valves, pumps, filtration tanks, et cetera. So we have dedicated teams of people like Ron and Samantha that have expertise across all the ranges of products that we sell. So Ron and Samantha are representative of a very large structure inside Harrington that's custom built to provide you with the advice and solutions that you need. They're there to support your local sales representative. They're there to support you. Reach out to your local Harrington team, tell them about the problems that you have and what kind of helps that you need, and they can pull in the specialist team. And then also, we have very strong partnerships with all of our suppliers, our supplier partnerships. So we also have the ability to leverage our partners and the manufacturing expertise that they have, and working together with our specialists to make sure that we have the right solutions and that we've selected the right products for you. Next slide. Single source, another key underpinning of Harrington. We have all of those solutions that we see listed there, and our goal is to make it so that you can get everything from us without having to go to multiple suppliers and get quotes from all different sorts of people. Next slide. Another thing that I wanted to highlight here, which you may not know, is that Harrington isn't just Harrington. Harrington is a large group of companies. We've been growing organically, but we've also been growing by acquisition over the last few years. And Harrington now includes this great array of companies under our umbrella. Pump Man Services for pumps, Aetna Plastics, Chris Group, J2. The key for all these companies is that they each bring a capability and expertise and a geographical coverage to our company. So each of these organizations expand the services and capabilities that we can bring to you, and they also give us more of a local presence to provide you with that better service. Next slide. And then finally, this is really just underscoring the size and reach of Harrington. We have offices around the country, and especially now with our acquisitions, this footprint is always growing. And in addition to stocking locations, we have a network of distributors throughout the country. So we can put product in a local office, we can put it in a distribution center, or we can put it in your facility, and we can make sure that you get what you need. And that's key to what we bring: the expertise, the 24/7 service, and the ability to custom tailor that supply chain for you. So large footprint. And again, I think through my year of being here, I don't think that many people really understand the power behind the organization that's supporting you locally and how that plays into our being able to serve you. Next slide. So with that quick overview, we'll give it over to Ron, the star of the show today, and he's going to take you through how filtration is critical to maintaining your cooling towers and improving their efficiency. Ron, take it away.
Thanks, Peter, Kevin, Samantha. Appreciate all of your input and help on this. So let me just apologize in advance. I'm going to be making you watch me as I talk. So without further ado, here I am. So great to see everybody. Really appreciate you attending this this first master class. We're looking forward to conducting many, many more. And as both Kevin and Peter mentioned, we have a fleet of specialists, all experts in their fields. And so I had it reinforced to me yesterday at a customer lunch and learn, an installer of equipment at semiconductor facilities up here in North Texas. and they were stunned. They looked at the presentations that we were giving and said, we had no idea Harrington did that. It's maybe part and parcel with the fact that we've done such a stunning job selling pipe and valves and fittings that's what people think of us as. But as you'll see here, we're much, much more than that. So without further ado, I'm going to go ahead and advance the slide, and we're going to talk about cooling towers, and especially how filtration will help with maintaining and keeping cooling towers operating at optimal efficiency. So cooling towers are an energy efficient, very environmental friendly method of cooling. We're not using hydrofluorocarbon-based cooling chemicals. Of course, now the industry is moving beyond those. But it's a non-chemical approach to cooling, basically through evaporative cooling. One of the interesting features of cooling towers is that even with the evaporation you would anticipate, there's not a lot of water volume loss due to the evaporation process. It's mostly due to a term that's called blowdown. And basically, as solids and dirt collects in the reservoir, the cooling tower, it has to be purged from the system. And so there's a wastewater loss associated with cooling towers that far exceeds this 1 to 2%. It expels heat into the atmosphere as water vapor, and it's often a first step to a cooling process that may be followed by secondary chiller systems that could be chemical refrigerant based. But they're used both for HVAC and for process water within facilities, and we'll see more about that in the next slides. But the first thing is to understand that evaporative cooling as a technology is nothing new. We're talking about a technology that has existed for better than 3,500 years. The Egyptians would put trickle water on mats in front of doorways and windows for cooling, of course, in the desert environment. And the Romans, 2,000 years ago, I snapped these photos on a visit to Pompeii, and I was stunned to see an advanced pipe infrastructure running cold to the houses. That in itself I thought was interesting. What I didn't realize at the time is not only did it power fountains and provide drinking and wash water, but they used the water running through floors in tubing and also in the walls for cooling purposes. And in the Middle East, they would use cooling towers. There would be wind towers running through underground cisterns and channels where there was water for evaporative processes. Very advanced, really, for the time. That the previous photo was from about 1,200 years ago. And there you can still find structures in the Middle East today, in India, Pakistan, Iran, in North Africa. I've seen some of these actually in Morocco. More recently, I mean, the technology never really did anything with that until about the Industrial Revolution. And so with the advent of steam engines, there was a real need to be able to recondense the water for reuse. And so in the 1880s, cooling towers were introduced as a method to do that. In 1918, the first hyperboloid cooling tower, the conical ones that you see today at power plants, that's when that was patented. Wood construction was the norm, and it was replaced by steel and concrete beginning in the 1920s. It wasn't until the 1950s that they went from a passive system to a system actually drawing air through the cooling tower using a fan. And then 60s, 70s, and 80s all saw their innovations. Now going forward, of course, everybody's aware that there's a lot of environmental activism, and there's a concern about anything that maybe alters even the immediate environment around equipment. And so, of course, these eject heat and water vapor. And so there's a move to reduce that and have a zero emissions system. We're not there yet. But then, of course, there's all kinds of automation that has been introduced as well. Well, just like Apple, in terms of the regulatory environment, there's an agency for that. There are a lot of agencies that have their fingers in the pie of the cooling tower world. The foremost among them would be, of course, the EPA, by virtue of the Clean Water Act, the Clean Air Act, and the National Pollution Discharge Elimination System, or NPDES, which regulates the discharge of waters off-site. Then OSHA gets involved, of course, for occupational health and safety for workers who work on cooling towers. CDC is involved. Everybody may remember the Legionella outbreak that occurred quite a few years ago. It was an unknown bacteria. It was a group of Legionnaires at a convention, and the convention center was cooled by a cooling tower with an open loop system where the evaporative air was pumped into the convention center, and the bacteria there caused respiratory problems for these people, and many of them died. And so now the CDC, of course, is regulating cooling towers, especially or primarily for HVAC systems. National Institute of Occupational Safety and Health is involved with the biohazards where workers are concerned. NFPA regulates fire safety. Local and state health departments, primarily the local county, city building departments, they're saddled with the obligation to enforce the regulations that are handed down from the agencies above, usually at permitting or registering cooling towers. And then the American Society of Heating, Refrigeration, and Air Conditioning Engineers, not a regulatory agency, but most regulatory agencies look to them for published best practices. I included the New York City Department of Health and Mental Hygiene simply because in all of the US, New York City, as you might expect, has the most registered cooling towers. They have about 5,000 on their registration list. So there are all kinds of cooling tower types and configurations. We can only really concentrate on a couple of them, and really we're going to concentrate on the one that is most common. So there are two basic types. The one that you see on the left is an open loop cooling tower. Hot water from the plant comes in, goes down through the dispersing elements, and has an upflow of air that causes evaporative cooling. That cold water then falls to the basin reservoir, and from there it's pumped straight back to the plant. That's an open loop. The closed loop, which is now by far the more common, especially in a new cooling tower application, I don't think you'll see any open loops ever again as new systems. The closed loop is a hot water pipe that comes in, much like the radiator of a car, back and forth until it's cooled by the same process. But now the water that's cooling is provided from the reservoir in a loop, and it is sprayed down over again the dispersing elements, and then drops into the reservoir. The big problem with, or feature, I guess you would say, of cooling towers is that they draw massive amounts of ambient air in, and that air is saturated with dust. Depending on where you live, you may be bombarded with dust and have to change filters in your air conditioner quite often because the ambient air is dust laden. Well, this just goes straight into the cooling tower and drops down with the water into the cooling tower reservoir and collects there. And it eventually will create a sludge layer at the bottom of that cooling tower reservoir. And there'll be more on that in a bit. Another thing is those dispersing elements, the cleaner they are, the more efficient they are. The nozzles that spray the water down on the dispersing elements, those can be clogged with debris. And so there's a very, very high level of need to keep that water clean. But by nature, it's drawing in all kinds of dirt, debris, organic material, bacterium, and other constituents that really helps if you can somehow clean that up. And so how the system operates, you have, as I described already, hot water comes in. Now I'm only going to show the closed loop system going forward, but the hot water comes in and the water coming down over it through the dispersal elements from the spray nozzles is cooled by heat exchange via evaporation, and it cools that water for future use within the plant. And then falls through the reservoir. And that video that's playing is an actual element. There are different kinds. There are honeycomb elements. What you see here is corrugated plates that are basically just creating more surface area so that the air has more opportunity to cause evaporation on the water itself. So if that becomes plugged, if it gets covered in some form of dirt, you lose cooling efficiency, and so you lose the very purpose why that cooling tower is there in the first place. And this is more of that description, and that the evaporation and cooling is again causing a heat exchange effect. The hot air is rising, cool water is dropping. There's a makeup water connection. And what's not shown here is there's always a drain so that they can purge the dirty water. And of course, as you can imagine, that can be quite a high level of water that has to be purged to drain the sludge out of that basin. And again, that's called blowdown, and that's referring to the sediment that is blown down into the reservoir. Sometimes there's not even a screen. I mean, the basin, the reservoir itself can be open. My favorite story was a municipality that I was talking with, who came in one day and the workers came in and found a dead deer floating in the cooling tower. Now, I've seen pigeons and other dead animals there. That's an exception, not the rule. But I mean, it's open to the atmosphere. You can get anything that's in the atmosphere or running around the facility into that basin. So what do we do with the cool water coming from the cooling tower? Well, again, there are several uses. It could be an air exchanger where it's actually exchanging air for HVAC purposes. Years ago, I had a facility that I opened up where we had a testing laboratory. It was a sales distribution warehouse. We had a training room and then a testing lab because we were certifying equipment that used methyl ethyl ketone, MEK, very, very smelly chemical. And in that lab, we had to keep a negative pressure on the lab, very slight, but enough to draw air in from the building into the lab so you could stand at the door and not smell the chemicals. You only smelled them as you went into the laboratory. Well, it was impractical to do that all through a conventional air conditioner, so we put a cooling system in, an evaporative cooling system, exactly what you see here, and then provided that cool water to an air exchanger, which then was further cooled by the conventional HFC air conditioner. And what that did was it allowed us to not expel tons of cool air up through the roof from the laboratory. So that's kind of an example of what you would use an air exchanger for. Now, the image you see here is a shell and tube heat exchanger. There are other kinds of heat exchangers. There's flat plate and all kinds of configurations. This is by far the most common. And so you have the cold water coming in from the cooling tower to a baffled system. And then you can't see it in this image, but there are tubes that are U-shaped that run through this with baffles inside of the heat exchanger. And then hot plant water is pumped in, cold water pumped out to the plant, and hot water coming back in from the plant. And then it goes to the top side and back to the cooling tower. So in essence, the cooling tower is a heat exchanger. The shell and tube heat exchanger is a heat exchanger, and it could very well be going to a compressor, evaporator, refrigerant-based system. It's just giving it a leg up on cooling, so energy costs are far less. It's far more efficient. They can also, within the plant, perhaps have a need for hot water. Well, you're producing hot water right there, so they can tap into that as well. So they could use both cool water and hot water from the system. Common water quality issues, I described some of them: dust, pollen, leaves, animal feces, or even animals themselves. Certainly insects, bird droppings. You can get microorganisms, bacteria, and algae into a system. One of the major concerns is corrosion byproducts, rust, scale, oxides and hydroxides that can gum up pipe and cause blockages within the cooling tower. So the implications dollar-wise is a clogged heat exchanger is something you have to clean out, and it could fail over time. Spray nozzles, as I described earlier, and the fill media of the water tower, the upper right image, you get reduced thermal efficiency. I don't know if you'll see it in the video down below. That's actually a video. This is a video of a maintenance crew trying to unplug, there you go, trying to unplug the heat exchanger, which is plugged by those solvents. And so you've got maintenance downtime where the plant's not operating. You have the cost of maintenance. You have the cost of chemicals because, of course, you need biocides and anti-corrosive materials, pH adjusters, anti-scalants, all kinds of chemical mixes, which we can talk about here. So you have scale inhibitors, you have corrosion inhibitors, pH adjusters, and actually, I think I've got my next one. No, more biocides, algicides, dispersants that help prevent the buildup of solids. And so chemical suppliers will often make custom formulations and then sell those in the totes that we saw on the previous slide to a customer. They're very expensive. I was actually at a semiconductor outfit up in North Texas that I asked if they had cooling towers. Yes. I asked, how much are you spending on chemicals? And he did the calculation. He said, well, the totes are $20,000 a piece, and we go through one every 2 months. So that's $10,000 of chemical expense every single month. And they shut down about every 6 to 9 months for 3 or 4 days of cleaning. So labor cost about $3,000. And the total annual spend of labor and chemicals was over $125,000. And so when you have a clean, it's obvious. When you have a clean cooling tower, you're going to use less chemicals. A lot of times, a lot of the chemicals that are injected in the cooling towers go straight into the sludge layer at the base of the unit. They're not doing anything other than being absorbed by the sludge and even the organics within the tower, but they're not doing their stated purpose. You're feeding the dirt. And so if you take that out of the equation, you can have savings of, well, I say between 50 and 75%. And let's keep it there just for example's sake. I've seen reductions as much as 90% in the field. But if we call it a 50% reduction, their annual savings in this scenario would have been over $16,000. More likely, they would have experienced the upper end number. 25 or maybe more $1,000 of savings. Well, the interesting thing about that is the system would have had an ROI, a return of investment, of less than a year, significantly less than a year. The capital expense would have been paid for in a few months. And then from that point on, the savings is all gravy. So filtration is obviously the answer. Removes the suspended solids. It'll deal with biological contaminants and debris. And if you have the right technology, you will even reduce the scale-causing constituents, thereby reducing the chemical cost for anti-corrosives and scalants. So filtration will prevent fouling. It reduces your chemical usage significantly, and the blowdown. If you don't have sludge, you don't have to open a valve and drain the basin of the cooling tower. You can almost eliminate blowdown as a factor. It'll extend the equipment life. It'll improve efficiency. If you don't have dirty spray nozzles and dirty dispersing elements, then your cooling tower is going to be that much more efficient. If your heat exchanger in the building is not clogged, you're not going to have to shut it down and force feed air and water through it to get it open. And it's going to preserve the life of your equipment. Very much reduced energy consumption. You're not pumping against scale. So you don't have that much, you're going to save on power where pumping is concerned. And you have less risk of biological fouling, which would be very important where Legionella could be a concern. So we're going to talk about water filtration. But before we do that, let's talk about air. As I said, there's a huge volume of air going into the cooling tower that's laden with all kinds of debris, solids, dust, and other contaminants. Well, if you screen it out before it even gets into the cooling tower, then of course you're going to deal with a lot of it at the air level, not at the water level. And so there are basically designed for cooling towers, there are screens that can be retracted up and down, but they will protect, there'll be a first line of defense to keep dirt from getting into the cooling tower. So there are 5 primary places where you would filter for cooling tower operation. Now, 4 of them are relative to the cooling tower. The other is relative to the plant and the heat exchanger. By far, this is the most common configuration. And also, by far, the most commonly used method isn't a filter, it's a separator. It works on centrifugal separation to spin solids within that unit, which theoretically is going to cause them to slough off to the side and drop down into a collection bell. And I just have to say up front, this is a very worst possible application. It's the very worst for a couple of reasons. I'll talk about the centrifugal separators. We sell centrifugal separators, and there are places where they're perfectly suitable. This is not one of them. But it is by far, if you go to brand new cooling towers and they have a filter on it, most likely it's not going to be a filter, it'll be one of these. So even if you encounter an existing cooling tower with one of these, the end user, the customer, would be best served by taking that out and putting in a different kind of filter. Now, this is a side stream filter, so as the name implies, it takes a side stream off of the recirculating loop. Now, this only works with closed loop systems. You would not see this on an open loop system. And it really, as I say, it doesn't filter the side stream water. It separates it from the recirculation loop. So you have your basin water. Let's call it 10,000 gallons for the sake of discussion. Usually you're going to want to, and we'll see that in a later slide, you're going to want to deal with that at 5% or 10% of that volume. So if you had a 10,000 gallon reservoir, you'd probably want 500 to 1,000 GPM of filtration. Well, your pump is going to be recirculating at far more than that. So in this kind of a scenario, a percentage of the pumped water, which is a percentage of the reservoir volume, is being separated. So you're treating a percentage of a percentage. You're not treating all of the water, so you're still getting solids and debris, sludge, and other contaminants back through those spray nozzles and over the dispersal element. So it's really intended to, over time, reduce the solids in the basin, but not really preserve the equipment itself. So even if you had the world's best filter in that location, you still would only get partial results. So many manufacturers who sell cooling towers, as I said today, will use this. So the pros is, the reasons you would consider this, it's the lowest cost. So somebody who's very cost conscious, this would probably be what they would go with, not realizing it's really not accomplishing their objectives. There's virtually no energy cost to operate it because it's using a side stream of water you're already pumping. So it doesn't have its own pump. But then, of course, as I already described, it's a very low percentage of water being actually treated, and it's not being filtered, it's just being separated. And it takes a long time to change out all of the water in the reservoir. It really doesn't do anything to reduce blowdown because you're still collecting solids in the basin. So I hope I'm not sounding too negative. It's just this is probably not the best place to filter your cooling tower. Another thing is that except for the action of water falling on the surface of the basin water, it's not agitating the sludge. It's not mixing up the sludge. So it's still collecting at the basin. You still have to open a valve and drain it. The best solution, it's not the last, but it's the best, is an actual recirculation loop where you have a pump drawing water through a filter that is then being filtered and returning to the basin. And so the basin water is what's being filtered, not the water that's coming down eventually through the dispersal nozzles. Now, the other thing is, and it's a best practice, it's not mandatory, but it would be highly recommended, is that you put agitating sweep nozzles in a frame, in a pipe frame within the basin so that they'll sweep back and forth and agitate the bottom of the basin. So if there is any sludge that builds up, it gets spun back into the water and removed by the filter. It keeps the basin completely clean, especially if you start with the clean basin. If you start with the clean basin, you will have absolutely no buildup over time. And I can say that with high confidence. An example is Harrington provided some years ago, about 8 years ago, a couple of filter units to Long Beach Medical Center out in California. They had a huge problem with sludge and algae buildup in their basin. And so they cleaned the basin, put in a recirculating filter. I honestly don't know if they put in the agitating spray nozzles. I know we recommended it. I checked on it, I'd say about 4 or 5 months ago. They've been in operation. They have not had to clean out that basin once in 8 years' time. They were cleaning it out every 3 months because of the buildup they had before. So it was highly, highly effective system. Now, in that case, we used a screen filter. In the image you see here, that's a media filter. Now, if you could call them cons, you have to have a pump to recirculate the water. That's some expense. You should put in sweeps. They're very inexpensive, but it's a matter of running the pipe and nozzles within the basin itself. That will be the best solution. And if you do that, you're not only going to eliminate sludge and for the most part debris in the basin water, you'll keep your spray nozzles and dispersal elements and equipment pristinely clean without having to crawl into the basin with a bucket and a shovel and clean it out periodically. And most likely you're going to see a reduction, I'll say, of 75% of your chemical usage. And remember, at least for the mix that semiconductor plant was buying, they're $20,000 a tote. It's a huge savings. And so we'll talk about some of the individual equipment as we go along. And then another option is full flow filtration, where the entire flow is filtered coming out of the pump from the basin and going down through the spray nozzles into the dispersing elements and back to the basin. Good, but not best. You are ensuring that there will be no solids or buildup to speak of in the nozzles and dispersal elements, but the basin is still open to that inrush air of dust and debris coming in with the air, and it's going to fall right back down into the basin. It's not cleaning the basin. So again, the full recirculation loop into the basin is very best option. And I already discussed that. So the basin sludge is still not going to be dealt with. You're going to still have to clean it by hand. You're still going to have blowdown by having to purge it. Now, there could be a concern at times that you might have contaminated water coming in. So city water is notorious for having at times high levels of iron and manganese, sometimes organics and biofilm. Iron and manganese would be a concern because, of course, that will cause a buildup on equipment. And it might be necessary to treat that. Really, the only real practical way to treat that would be with a media filter. Perhaps some cartridge filters could help, but media filter would be more typical. I can't think of any solids that would be so significant that you would need anything other than maybe a manual screen at this point. But the concern would be if you have entrained chemicals, a media filter with the right chemistry and the right filtration rate will deal effectively with iron and manganese. Those are the two big ones. It's kind of an expensive thing. To be honest, I don't think we would see this very often, but I had to bring it up because of this potential that, a potential spot where filtration could be desired. To reduce chemical constituents, you would have to have some chemistry. We need oxidation. Usually that's accomplished by a small dose of sodium hypochlorite. If you had organics concerns, then a carbon system might be indicated. We can help with best recommendation for anything that you might come across. So if you do have an application and want basically some input as to what would be the best filtration solution, we'll make the recommendation. Now, whether it fits within budget, we'll see. If we have to compromise because of a budget or because of other sensitivities, we can take that into consideration. But we have the expertise to fully guide you on the best technology for a cooling tower application and heat exchanger for that matter. So how do you size your filter? Well, you can do that the hard way or you can do it the easy way. I recommend the easy way. This formula is basically the common formula that allows for variations in intensity of incoming debris. I actually created a spreadsheet so I could test the formula. I didn't like the results. It came up very, very much on the low side. So in the past, the recommendation was 2% of your solids, or I'm sorry, your reservoir volume. Well, running this calculation, that's exactly the number I came up with. It's totally inadequate. The best general rule of thumb I mentioned earlier is 5% to 10% of the total basin volume. And as the example I gave, it's 10,000 gallons would equate to 500 to 1,000 GPM. That also equates to about 3 to 6 basin changeouts per hour. So, when you think of air conditioning in a room, the major consideration is how many times do we exchange the air within the room. And that'll give you a number of efficiencies. So I would highly recommend, just as best rule of thumb, unless there are other considerations, that we just use 5% to 10% as the best approach. So then the last of the places where you might effectively, other than within the plant itself, there are a lot of opportunities within the plant itself, is the heat exchanger, from the heat exchanger to the facility. So, you could have scale solids, you could have byproducts of whatever processes within the plant that you want to get out. And you could, if you wanted to, you could put it on the hot water side, but you better make sure you've got something that can handle that temperature. So in the image you see there, I've got a high flow multi-round cartridge that can accommodate high temperature pleated cartridges. Polypropylene typically is good for up to 175 degrees Fahrenheit. You can conceivably see more than that on that hot water loop. So just something to take into consideration. But the filter is there to protect your plant equipment and also to keep the plant side of the heat exchanger clean. We're already, if we have the right filter on the cooling tower, we're keeping the cooling tower side clean, but that heat exchanger has two sides. So what type of filter? Well, there's so many variables there that they kind of boggle the mind, but what place in those of each of those 5 locations are we talking about? What is the contaminant load? What's the dynamics? What's the specific gravity of your contaminant load? What's the load and volume in parts per million, or same as milligrams per liter? Any chemical constituents that you're having to deal with, corrosivity issues. If we can get some water information, we can run a Langolier index and tell you precisely how corrosive your water is going to be. So particle distribution analysis would be nice to have, not absolutely necessary, but it would tell us what percentage of the solids are at what size in terms of microns. And it might help dictate what kind of micron target we have. What do you want? How pure do you want the water? What's your footprint? What can you do footprint-wise? I mean, if you have all kinds of space, great. If you don't, then we might select a filter that has a very small, perhaps horizontal and width footprint, but maybe makes up for it in height. So there are a lot of considerations, and what kind of energy are limitations do you have? And what can you afford to do in terms of chemicals and periodic maintenance? What's your interest in ROI and budgetary implications? So we have all kinds of, as I said, filter options that we're going to talk about. We're going to go through them very quickly. We have about 15 minutes left. And then we do want to open up the floor for questions. But there are cartridge filters and bag filters, and there are housings for those of all kinds. There are high flow cartridges, there are standard round cartridges, there are single cartridges, bag filters, again, of all descriptions, all materials, lid types. You can have a hydraulic, if for very large ones, a hydraulic lift davit arm, so you're not breaking your back trying to open the thing up for maintenance. One of the things on, say, a vertical is the one you see open in this image. Harrington sells structures, fiberglass structures. So somebody's going to either have to have a step ladder, but more conveniently have a structure next to that to be able to step up in onto for services purposes. So that's something to bear in mind. Self-cleaning screen filters, one of my favorites. And in fact, you remember that Luke that had the centrifugal separator, and I mentioned it was inadequate. Still going to talk about that. But the best solution would be one of these. And so they come in all kinds of configurations, and several vendors out there, and we represent some of the primary vendors. But there are verticals, which tend to be smaller for flows up to about 400, 450 GPM, and then horizontals, which will accommodate flows into the 8 or 10,000 gallon range. The way these work is you have a coarse screen on the left, a fine screen to whatever microns down to 10. Then the vacuum nozzle array, it has its own turbine. It's driven by water and a piston to move it back and forth. And so as water is flowing through the screen on the left, it goes through the coarse screen, out through the fine screen is filtered, as I said, down to 10. When it gets dirty, differential pressure triggers the cleaning mechanism, which moves the system forward and rotates it and vacuums the water to waste. And it never stops producing clean water while it's purging. It's not a backwash. And there's a huge difference between a backwash system and a purging system like this. A backwash system, like a media filter, is going to consume thousands of gallons, in some cases, many thousands of gallons of water just to backwash the media. It has to go somewhere. It's got to go to waste. So you have a significant wastewater cost. When this cleans itself, regardless of the size, the maximum loss of discharge water to bring it back to a pristinely clean state is about 45 gallons. It's a 15-second vacuuming cycle. The operator is not even aware it's doing it. I mean, if they put their hand on it or if they take the controller and put a light on it, they'd know when it was purging. But if they put their hand on it, they could feel it vibrate. But that's basically the only way they would know that it's cleaning itself. It just does it and keeps doing it until the cows come home. Not much to do on them for preventative maintenance. I like to have people inspect them once a year. Frankly, in my experience, nobody does that. And they just keep on working. They're a very bulletproof kind of a system. Very, very much a fan. As I mentioned, we can get screens down to the 10 micron range. For cooling tower purposes, a spray nozzle has an 80 micron orifice. So I think probably best target would be a 50 micron screen. You can use those in virtually, I got ahead of myself, but you can use those in virtually any of the filtration scenarios that we've talked about. Then we have depth filter and specialty cartridges. Depth filter just means it's a melt-blown polypro usually cartridge. The filter progresses from a coarser fiber to a finer fiber, and that just gives you longer life on the cartridge. You can get very cheap filters that come from Amazon or Asia, but they're mostly a uniform blown. They don't have this feature. It's not much more. These, in some cases, these are $2 or $3 filters. Then there are pleated filters. Of course, the high flows would be a pleated, and they come in different materials, different porosities, different lengths. Very, very popular in process cooling water loops. So I would imagine that you would see a pleated filter quite often in one of these applications. And that's fine if they're in the 1, 5, or perhaps 10 micron range. That's a good solution. If it's much larger, and a lot of times we'll see 50 micron process cooling water high flows, I'd recommend a screen instead, simply because it is self-cleaning. You don't have a consumables cost. But pleated is basically taking a material and then compressing it like on the hem of the skirt so that you get more surface area, and therefore you're not, you've got a prolonged life. carbon block for removing chemicals like chlorine or VOCs or organics. That compared to a media filter, a carbon block has the advantage. If you've ever gotten a Brita filter, you know, one of those countertop carbon filters, and you poured your first batch of water into it, you got all kinds of black silt. You have to rinse it several times before you can actually use it. Well, media systems are like that. But a carbon block is an impregnated resin. You don't ever get any release of the carbon fines into the final water. So for lower flows or for multi-round flows, it could be a good organics solution. Bag filters, very simple. It's a bag of varying sizes and all kinds of materials. I think it'd be useful to note that they're inexpensive. They're basically a throwaway. They can accommodate very high flows. We can get bags in the 1 to, well, even 1,000 micron range. But we do have oleophilic bags, so you can remove trace oils if that's a concern. And then also extended life and multi-layer where you have that gradated effect in the bag itself. And for bag filters that come in a wide variety of sizes. The most common one is the number 2 bag. I've seen that more than anything else, but number 1 and number 4 are also common lengths. And then media filters. Far too much to talk about here, but sand media would be very popular for cooling towers. That was one of the previous images I showed, was a skid with a sand media filter on it. Carbon filters, specialty media for heavy metal removal. If you had a specialty media like a Green Sand Plus filter, it would be a taller filter than what you see here, but it would filter down into the sub-micron range if the water chemistry is right. But that's really not the concern. It's there more for iron, manganese, and other heavy metals. Now, none of those will do anything about with scalant or corrosive, scalant causing components like silica, magnesium, calcium. Even a media filter is going to have virtually no effect on that. The centrifugal separators, the way they work, water comes into them. It's usually pushed down to increase the velocity, like putting your thumb on a garden hose. The bell is often offset, so it starts a centrifugal action, and the high velocity water spins around the unit along with the sediments in it, and it hits a bottom plate, and then there's no baffle or tube in it. It's all hydrodynamic action. It creates a path through the center where clean water can come out. And the solids will collect in the collection bell down at the bottom. Now, these are great. For instance, if you have a well that's producing sand and you don't want to put it into a pressure, bladder tank, pressure vessel, you can run it through a centrifugal separator. It'll draw out the sand. You don't need a more advanced screen for that. These are not ideal for cooling tower operations because they are dependent on the weight of the solids. And solids come in all types and kinds. You have gravel, sand, fine silt, which is very light, usually is entrained in the water, clays, algae. Well, a centrifugal separator will not remove anything that has a specific gravity under about 2.2. So for reference, beach sand has a specific gravity of 2.65. So if you have high enough velocity, you can still get some separation at a specific gravity of 2. But size and specific gravity don't go hand in hand. You can have something very big that's very light. You can have something very small that's very heavy. So people will specify a centrifugal separator and say, I want 80 micron separation. You can't tell what size of separation you're going to get. You can only tell what specific gravity you're going to remove. And so if you have, let's say and the question is, what do you suppose the specific gravity of algae, of silt, of floatable debris is? It's less than 2.2. And so a centrifugal separator is not going to draw that out. The only thing a centrifugal separator is going to do for you is high weight solids like sand or grit. It'll do nothing with the entrained solids. There's a very scientific method for finding out what a centrifugal separator will do for you. You take a jar of your water, you shake it vigorously for about 15, 20 seconds, set it down, let it rest for 2 minutes, and what settles at the bottom is what the centrifugal separator is going to get out. What's above the sludge layer that you see form at the bottom within 2 minutes is going to go right through it. And so you can test. I mean, if you do want to try a centrifugal separator, you do want to try this test. I mean, all you need is a mason jar, not real technical. Electrocoagulation is very popular today, and to be honest, if you do have a hardness challenge, it's a very good way to reduce your chemical costs. And essentially, it's an electrolysis-based system. You have two elements, an anode and a cathode, and it will reduce iron. Well, usually they're iron or aluminum, and they're sacrificial. So it'll release iron or aluminum ions into the water, which will congeal with the solids and form a flock that'll drop out. And in fact, it'll drop out into the bottom of that, but the ones that are still entrained will be so easy to filter, it'll highly increase your filtration efficiency. But above and beyond that is it takes out the three bad boys of scale, and that's silica, magnesium, and calcium. And of course, there's an energy demand, not high. But basically, you're causing a sludge to form, and there will be a lighter flock layer, which it will not remove, but that can be easily removed by post-filtration through a screen or a bag filter or a cartridge filter or even a media filter. And the last one is germicidal UV systems. If you have an open loop HVAC system, and the CDC requires at least annual testing for bacterial levels, and you're still concerned about the Legionella bacteria, or for that matter, any of the other bad guys, well, you can go ahead and run a UV system as a post-treat. The UV system that really only applies if you do have an open loop HVAC type system where people are going to perhaps be breathing in some vapor, but you can sanitize it completely with this. But the reality is, if you have a clean tower, if you have a good filtration, you're going to have only trace chemicals you're going to need to feed. And that is going to, for all intents and purposes, it's going to also sanitize your tower and eliminate bacterial concern. To summarize, clean water dramatically reduces chemical demand, blow down the wastewater that's drained off of the reservoir, maintenance costs, system downtime. It also improves the system efficiency and life and can save thousands, tens of thousands of dollars at times in monthly chemical costs and regular PM and cleaning, system repair. It'll make your system last longer. It has a stunning return on investment because the filters, even when skidded with pumps, just not that expensive. And in most cases, you can anticipate an ROI of a year or less. So we can open it up for questions. Very much appreciate everybody's attention and patience. And so with that, Peter or Kevin, if you'd like to take that over.
Sure, Ron, it looks like we have a couple of questions that came in. One you touched on a couple of times, but this came in earlier. What about silica?
Yeah, so silica we dealt with the electrocoagulation discussion. So electrocoagulation would be a good resource. Another which Harrington offers is ion exchange. And I didn't feature that in this discussion because the reality is electrocoagulation is far more commonly used, and that will deal with silica.
And Ron, to follow up to that, there was a question about using ceramic filters.
Ceramic filters would come into play when you have a high temperature requirement. And yes, you could use those. You would normally find those more in the plant production side than even in the heat cooling loop of the on the plant side of the heat exchanger. You're generally not going to see temperatures high enough to warrant ceramic for those locations. Certainly in the plant side where you have very high temperatures, yes. Not only those, but perhaps stainless steel or other tungsten or other metal type filters. But I guess that also brings up the point that, as we said, Harrington is so versatile with our offering. We have so much that we really couldn't discuss all of it here. So we covered really the key technologies that are used. But if there is a need for some other technology not discussed here, well, don't count us out. I mean, we didn't talk about RO membranes. We didn't talk about, again, ceramic or the metal filters. So there's far more to us than even what we shared here. Just not enough time in an hour to talk about it.
Ron, we had one other question, and it was, what about using glass versus sand in a media filter?
Yeah, you can use sand or glass, and it has some interesting characteristics. There are all kinds of media. There's catalyzed manganese dioxide, which is green sand. The reality where sand is concerned, if you a sand filter typically is not going to reduce beyond 25 micron at best, generally more like 50 micron. At that point, you're better served in terms of cost and footprint to go to a self-cleaning screen filter. But the glass media filters, there are all kinds of specialty media like silver dioxide and a lot of proprietary type media that floats around out there that can just as well be used, and some of them may have good application.
Any other questions from the audience? Those were the two that had come in via the chat, but we have another minute. I guess Ron can stick around if there's any more. Otherwise, we can wrap up.
And Kevin, there was a question about will there be a PDF of the slide deck to go out?
One came in through the chat. Peter, is that something we're going to provide, or can? I would assume we could.
Yeah, so what we'll do is we have this recorded, obviously, and what we'll do is we'll make it available via recording on YouTube, and we'll share it with our social media for anybody who wants to rewatch it, or also for anybody who couldn't make it and had registered for it. In terms of providing the PDF, that's normally not something we do to do a publicly available PDF file. So I would have to decline on that one.
Yeah, you certainly can reach out to your Harrington office and get additional information if you have any more questions, and they can share more information with you through that channel as well.
Yeah, and I think I mentioned earlier about yesterday I did a lunch and learn, and I actually used some of this material, not all of it, for the presentation. It just applied where I was at. For those of you who are customers, or even the Harrington sales reps that are on, be sure to reach out to your specialists, not just the filter specialists, but your pump and all the others, and have them come along and do lunch and learns for you. You'd be amazed at the light bulbs that go off with customers. Yesterday we had 3 of our specialists, not just for filters, but tanks and high purity. And it was a pretty lively discussion. So again, if you are a customer and would like to have us come and do a presentation, we're more than happy to do that.
And I had a question come in about, being invited to additional classes in the future. as we do these in the future, we have collected your email addresses, I guess, for those that registered here. So you should now be part of our email list. And then, when you get those emails, you can register for the future classes at that point. So we'll keep you in the loop.
And Ron, there was one more conversation that came through on the chat regarding if we had any documentation on the electrical coagulation for silica extract.
What kind of documentation are we looking for?
Might be easier if we just grab Brandon's contact information
yes,
and reach out to him directly.
I see the chat. Brandon, I'll reach out to you.
All right. If we don't have any other questions, I think we can wrap up. We appreciate everybody attending today and look for future events. Thank you.
Just one quick comment before you pop. I'm just throwing our email addresses in the chat as well. We could have put those up on the screen. We should have put that up in the end. But if you have any questions or comments or things that you want to reach out to with more information, please do reach out via email.
Of course, contact information for all of our local offices can be found on our website at hipco.com. Any of our branches can put you in touch with, any of our specialists, whether it's filtration, instrumentation, pumps. They're all readily available to support, the full field salespeople in all of our locations as well. So.
All right. Great. Thank you, everybody.